Hey, welcome to Deep Learning Explainer. Today our topic is quantifying attention flow in transformers. This paper is published by the people at University of Amsterdam. This paper tries to address one of the biggest problems of analyzing attention weights in transformer. Analyzing attention weights is actually the most straightforward method to interpret attention models like transformer. But the problem is when you analyze the higher layers in transformers, the attention weights it actually got mixed. What I mean by that, for example, if you analyze the attention weights in the first layer of transformer, there's actually no problem at all, because when the model pays a lot of attention to, let's say, token number 4, then the model actually pays a lot of attention to token number 4. But when you go to the higher layer, for example, second layer, when model pays a lot of attention to token number 4, it actually not only pay attention to token number 4, it actually pays attention to the linear combination of other tokens. And how we calculate this linear combination is actually we need to trace back to the first layer's attention weight, because the way model combine the representation of other tokens is actually according to the attention weight in the first layer. So as you go higher and higher layers, then your attention token identity actually got mixed. Token number 4 here is not only token number 4 anymore, it's just a very complex linear combination of other tokens. So how to address this problem? This paper actually proposed 2 methods to address. Before we dive in, if you would like to receive more deep learning videos like this, don't forget to subscribe so you can receive relevant videos in the first place. And your subscription is my greatest support to make more videos like this. So thank you for your subscription, and without further ado, let's dive right in. And the solutions proposed by these papers there are 2. One is called attention rollout, another is called attention flow. Basically, they all are ways to trace back attention flow to your original input tokens to better understand the attentions. Before we explain those 2 methods, I want to clarify the terminology they use in this paper. So first one is attention weights. Attention weights don't mean the attention matrix in attention layers. What it actually means is attention value that they calculate after the attention by attention layer. So for example, if your input tokens are these, then after one attention layer in the BERT model, other transformer models, you will calculate attention value for each tokens, and the sum of these attention values will be one. So it's a kind of a normalized value to tell BERT models how important the token is. So in this paper, they call this attention values, attention weights, and I will also be using this terminology, attention weights, later on. And another terminology I want to address is input embeddings. So basically, in the first layer, you can say your input is token, like in this example, token he was something. But after token 1, your input is not your input token anymore. So what's your input is? Your input actually called input embeddings. Actually, I prefer call this like input position, but you can, in this paper they call input embeddings. I will also use these 2 different ways to address that interchangeably later on. So for first method is attention rollout. Attention rollout is basically has an assumption that the identities of input tokens are linear combined through the layers based on attention weights. So if you find out a way to linearly trace back to your input tokens, you will be able to recover the real attention weights in the layer you are interested in. So how they do that is actually quite straightforward. It just you do the recursively multiplication through layer and until you reach the first layer. So for example, if we want to calculate the effective attention weights in the layer 3, third layer, then we need to calculate the attention weights in second layer and also calculate attention weights in the first layer. So it kind of multiply back to until you reach the the first layer. So it's a little bit like the big forward way to chase the attentions, and it's very intuitive. And there's one thing that you need to be aware of, which is residual connections, because in the transformer models there are a lot of residual connections. So what the residual connections are, they are actually pretty simple. They just let's say your input is X, then your eventual output will be actually X being processed by the function f plus your original input X. So your output is not only being processed by function, you need to do the addition with your original input X. This is just a way to let the models to connect to the original input in a more natural way. And it's widely used in a lot of tasks like computer vision. So if we write down this in a neural network matrix manner, then you will find out it's actually your output V matrix is like your input to multiply with your attention matrix and plus your input. Then your effective attention matrix is basically equals to your original attention matrix do the average with your identity matrix. So this is just something when they calculate you need to be aware of if you want to implement this attention rollout thing. And one thing worth mentioning is they can actually use this way to analyze each attention heads in every layer. But to make it simple, they just average the attention weights across different attention heads. But you definitely can do attention heads by attention heads, and they also have this in their appendix. Another method to trace back the attention weights is attention flow, and it's basically it assumes that the attention weights represents the capacity of the attention flow. Is the maximum the attention can flow through, but it's not necessary to be it actually flows through. And they use the maximum flow algorithms to compute the max attention flow. Okay. As I'm not that familiar with graph theory, you may need to find out more reference to understand the maximum flow algorithms to understand the implementation or the better concept of it. But the idea is there. It's basically the way to chase back the attention, recover the attention weights in higher layer by adding the attention weights or using other similar methods from the preceding layers of BERT. So let's talk about the experiment setup. This paper used experiment to kind of verify if there's a very strong difference between using the raw attention or attention rollout and attention flow. So the task they did was the verb number prediction. It's very straightforward. Basically, you need to, giving us context, you need to predict if the verb of the subject should be singular or plural. So it's viewed as a classification task. You got a context, you do the binary classification to see if singular or plural. It's like this. The key to cabinets should be a singular, right? Is or some other singular verb. And the BERT model will, the actual input of the BERT model is you will have the classification token to tell BERT this is a classification task, and the rest of context. Then predict if it's a singular or a plural. And as you may know, the BERT usually when we plug in this classification token means we will use these tokens, classification tokens representation in the last layer as an input of prediction layer, which is a feed-forward neural network, and to let model make the final decision. And this is the raw attention maps for classification token. Meaning when BERT is processing this classification token, how it pays attention to other tokens in different layers, or you can say other token position in different layers. And it's quite obvious that above the layer 3, the attention that BERT pays actually is just uniformly. It just super uniform is not paying particular attention to anything in the higher layer when the layer is above 3. So it's pretty weird because the main purpose of attention is like you pay different level of attention to different words, because some words are supposed to be more important than other words, but we cannot see this kind of phenomena in the higher layers. So there could be two possibilities, right? The first one is BERT just fail to learn how to pay attention, and second possibility is maybe we view the way we view attention's weights is just wrong. It's not completely proper. That's also the main point of this paper. So two methods they propose. They also visualize that. The first one is attention rollout, and you can see as you go higher layers, BERT actually pays attention more strongly in the important words. Like this example, the key to the cabinets. The most important word that you should pay attention is supposed to be key, right? The key is the subject of this verb, and it's the most important thing that you need to know. Is singular, so the verb should also be singular. And you can see when you go to the last layer of this model, and it actually pays very, very strong attention to the word key. And same goes to other examples as well. And you can see that it goes to higher example, it pays attention to certain important words more. And also you can see the similar pattern in attention flow. When you go to the higher layer, it kind of pays stronger attention to important words. And you can see some subtle differences between these two methods. Attention rollout actually pays more attention to the very important word key. And attention flow, if you use attention flow to view it actually pays attention to the key to it, which is surrounding word to key, the and the to. It's not the most important, I will argue. To really quantify the usefulness of attention weights, this paper uses this very interesting way to do that. There are three steps. The first step is basically you need to calculate the importance of the token and to see if BERT actually pays more attention on the important tokens. So the first step is just need to calculate the importance of token. And how they do that? What they do is to basically to blank out the tokens one by one, and because it's a classification task, so when you blank out one token, you can see how much it affects the classification accuracy. If it affects a lot, that means this token is important. So they basically use this principle to calculate the importance of token. And the second step is to calculate the attention weights of the token, and when the BERT is processing the classification token. So basically just like what you saw in previous slides, it's like how much BERT pay attention to tokens in this given input when process the classification token. And the last step is to calculate the correlation between token importance and the attention weights to see if when the token is more important, it actually gets more attention. And definitely there are three different ways to view BERT's attention weights. One is just to use the raw attention weights, and the rest of two is just to modify to calculate the effective attention weights. And as you can see, if we just use the raw attention weight to view it, and the correlation between token importance and the attention weights just only obvious in the first layer, and in the layers they are above first layers, they are just barely have any correlation between importance and the attention weights. And if we use the kind of the proposed methods to view these attention weights, you can see as you go to the higher layers that there are actually very, very strong correlation between token importance and the attention weights. Means if this tokens is more important to the classification task, then it got more attention weights, which makes sense. And what it tells us is actually the BERT actually pays a lot of very strong attention to important tokens. We need to use the right way to view it. I would really agree that the attention rollout and attention flow is a very important way and also mathematically reasonable to view these per attention weights, and it just also reflects to our intuitions, like it actually pays strong attention to important tokens. By the way, the slides that you see before these slides, the model they use or is GPT-2, and they also did another experiment on the distilled BERT. So it's they fine-tune distilled BERT on sentiment analysis, sentiment classification data, SST2, and to see, use the same methods to see how much the correlation between token importance scores and the attention weights, with these three different point of view of attention weights. And the results are quite different from the previous one. Previous one, you can see there are strong correlation in the last few layers in the attention rollout and the attention flow point of views. But in this experiment, the difference between the raw attention and the proposed methods is just not that big. It's not that big. But even though you can still see the correlation between them are still exist. Like in these last two layers, attention rollout and the attention flows correlations score still higher than raw attentions. So it's still I would say it's still a better way to view attentions. And there was another showcase. Basically, is they try to lay the BERT model, pre-trained BERT model, to do the pronoun prediction. They feed the BERT model these two sentences. So basically, these two sentences are interesting because you can predict both female or male pronouns. They both will be correct, just depending on how you think this pronoun is referring to. It can be referring to Sarah. It can be referring to Arthur. So the Arthur talked to Sarah about blah 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 book, and in this case, the pre-trained BERT model think these pronouns should be his, should be a male pronoun. And if BERT thinks this is a male pronoun, then BERT probably think this is referring to the noun here, Arthur, the Arthur. So we should see BERT pays more attention to the token Arthur. And there's a comparison to see if BERT is paying attention to Arthur more or Sarah more. And indeed, when BERT thinks this is a male pronoun, then it actually pays more attention to token Arthur. No matter what kind of attention views you use, even you use the raw attention view to view it, it still pays more attention to Arthur. So this kind of makes sense. And one thing worth pointing out is when you use these two proposed methods to view it, BERT looks like paying more attention to Arthur, the token Arthur. So that's another evidence to say that proposed methods are better. And another example here, Mary convinced John of blah 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 love. And in this case, BERT thinks this pronoun should be her. Mary convinced John of her love. And if BERT thinks this is a female pronoun, then most likely BERT thinks this pronoun is referring to Mary. And if we look at the attention map, raw attention map here, you can see BERT actually looks like pay more attention to John. And if we look at the attention rollout, it also looks like BERT pays more attention to John. And only when we view it with attention flow, and BERT looks like paying more attention to Mary, which makes more sense. So this is just some we can see there's still some difference between attention rollout and the attention flow, but still there's very hard to say which one is better, because they both simplify a little details of tracing attention flow. But one thing we can know from these so many experiments here in this paper is these two methods are indeed really good. So the key takeaway for this paper is there are actually a better way to view attention weights, and it's not really difficult. It's simple and also effective. there are so many attention. So many people actually analyzing BERT's attentions, but I think it will be very important to be aware of the raw attentions, the problem, then using this kind of improved methods to examine that in a more accurate manner, and we probably will have maybe better insights of how BERT actually paying attention. So that's all for today. And if you would like to receive more deep learning NLP videos like this, don't forget to subscribe so that you can receive the videos in the first place. And other than that, enjoy your weekend, and I will see you next time.